Okay, so now we're going to talk about nitrogen nucleophiles here, reacting with aldehydes and ketones. Okay, this is going, so when you have a primary amine reacting with an aldehyde or ketone, you form something kind of weird, which is called an imine, right? So not an amine with an A, but an imine with an I. And notice that what we've done here is essentially taken this oxygen and replaced it with our nitrogen, but then nitrogen likes to have 3 bonds, which is why we got something sticking off of there. Okay, so those are what these reactions do. Unlike before, unlike a lot of the reactions that we see where you form an alcohol with your ketone oxygen or aldehyde oxygen or carbonyl oxygen, here the nitrogen completely replaces the oxygen, okay? Real quick, I just want to make a point that we say that these reactions are acid catalyzed, and they are, but not in the same way that we were talking about mechanisms under acidic conditions. Okay, it's kind of weird because an amine is a base. So you have to have a pH that isn't too low. Otherwise, you'll protonate the amine, making it an ineffective nucleophile. But you can't have your pH too high because otherwise there isn't any acid to catalyze this reaction. So this reaction takes place best around pH 4 to 5, which is technically acidic conditions, but really, I mean, I think about it more as being neutral conditions. And because of that, we're going to see both positive and negative intermediates in these reaction mechanisms. Okay. All right, so again, we're going to form this imine here. Let's see how that happens. So first step is we have our nucleophilic nitrogen going and attacking that electrophilic carbonyl carbon. And notice, because we're at neutral conditions here, we have a negative charge on our oxygen right next to the positive charge on our nitrogen. Okay, so these aren't, again, just sort of distinguishing what we were talking about before as acidic conditions and basic conditions. These are now neutral conditions where both of those charges are possible. Okay, the next step is going to be a proton transfer that happens to that oxygen, as well as a proton transfer removing a hydrogen from that nitrogen, right? So we get to this step here. We have to protonate the oxygen and deprotonate the nitrogen. To be honest, if you, instead of using this, you know, whatever generic acid, generic base thing, if you wanted to have the oxygen reach over and grab the hydrogen off of the nitrogen, that's okay too, right? So you could do these 2 proton transfer steps in one, whatever you guys want to do. And now we get to what's called a carbinolamine, carbinol for the alcohol group, and amine for the amine group. But these are not stable. So your carbinolamine does not last. What ends up happening is the oxygen gets protonated again. What do we know about these groups right here? It's now a really good leaving group. So the next step is going to be this pair of electrons on the nitrogen comes down and kicks off that leaving group. Notice that that forms a nitrogen carbon double bond. All right, so then I'm almost to my imine. The last step is just to deprotonate that nitrogen. And that's how I get to my imine. Okay, so you see that we've effectively kicked off that oxygen altogether, kicked it off in the form of water, protonated it once to form an alcohol, and then protonated it again to form water, kicking it off. Okay, yeah, again, just to hammer this point home about the pH, you can't have these under like absurdly acidic conditions because most strong acids will just react with your amine to form an ammonium ion. And the ammonium ion is not reactive enough for this first step here. It's not a good enough nucleophile. So again, these reactions have to take place with your pH in that perfect region around between 4 and 5, which we're going to call a neutral reaction mechanism, meaning that you're allowed to have both positive and negative and of course neutral intermediates. That was what that word there was, even though you would have no clue because it was so messy. Intermediates. Okay. What do we get when we have a secondary amine? So that was always primary amines, right? We'll form the imine. If we have a secondary amine, we're actually going to form what's called an enamine, which is a double bond. That's the ene portion. It's actually color code. Next to the amine group. So an enamine is what happens when you have a secondary amine reacting with your aldehyde or ketone. Tertiary amines will not react with aldehydes or ketones. So it'll be either primary or secondary, or if you're ammonia, you would form an imine. So let's see the reaction mechanism for this. It's going to start out much the same. First step is going to be nucleophilic attack of that electrophilic carbonyl carbon, bumping that pair of electrons. Again, because this is neutral conditions, I'm going to get this intermediate that has both a positive and negative charge. So I'm going to need to deprotonate the nitrogen and protonate the oxygen. The book does it in 2 steps, but if we're going to be lazy, we'll do it all in one by having the oxygen, having the oxygen reach over and grab the hydrogen from the nitrogen, right? So that takes us directly to this step here. Or again, we have that carbinol for the OH group, amine for the amine group, right? Located right next to each other. Again, though, these aren't stable. So the next step is going to be protonation of that alcohol oxygen. This forms our really good water leaving group. So the nitrogen is going to put that pair of electrons down to kick off that really good leaving group. So now we're here, okay? The difference before is that we had a hydrogen on this nitrogen, so we could just deprotonate the nitrogen. Here we don't have that, right? Because it's a secondary amine. So instead what's going to happen is a base is going to reach, some basic species is going to reach over and grab this hydrogen. That pair of electrons is going to come down, allowing the pair of electrons in that double bond to come up. That's how we get our enamine at the end. Okay. I know it always kills people when we use these like generic acid, generic base sort of things, because they're always like, well, what is it? Well, that really sort of usually depends on what solvent you're using. So yeah, you're just going to stick with generic acid, generic base kind of format here. Okay, and again, reaction mechanisms very, very similar. We get to this step here where we have this nitrogen double bonded to our carbonyl, what was our carbonyl carbon that has a positive charge. In the case of a primary amine, right? So that's what this is primary amine. That nitrogen gets deprotonated and you're left with the case of the primary amine and you're left with the imine. In the case of the secondary amine, you can't just deprotonate the nitrogen. There's no more protons there. And instead, you're going to lose that hydrogen on the neighboring carbon and form the enamine. Okay, so primary, you get an imine. Secondary, you get an enamine. Mechanisms are really super similar, except for that very last step. Okay, this is another example. So first of all, if this is going to be my nitrogen. Notice that this is a lot like a primary amine. I know there's another one on the other side, but this is a special compound called hydrazine that will react with the ketone or aldehyde to, again, form our expected enamine, our expected imine. The reason why we're learning about this is a special kind of reduction, which on a second step, you can use basic conditions, water and heat, and cleave that enamine group off, okay? Again, effectively, the whole point of this reaction is now we have a second way, in addition to our thioacetyl reactions, to just cut that oxygen altogether off, replace it with 2 hydrogens, all right? So accomplishing the same thing as that thioacetyl reactions. And just note that these reactions are readily reversible. Every step in our reaction mechanism was reversible. So you can have acid catalyzed hydrolysis of an imine or enamine to a ketone or aldehyde. All right, so just to summarize here. So again, the question always, do we have to know a mechanism? Yes, for the formation of imines, as well as enamines, and even the reverse direction as well. You do not have to worry about it for this reduction reaction. The whole point of that was, again, we have a way to go from ketone or aldehyde fully reduced to an alkane.